Hello, everyone. Thanks for attending Build Better. This is a session about the practical framework for evaluating AI tech for execs with no time. So I really appreciate, since the audience is people who have no time, really appreciate you spending time on attending the session and Build Better. So two words around, about me, not to waste a lot of time on this. I'm Simon. I'm founding machine learning engineer at Instrumental, currently leading ML at Instrumental. And before that, I was doing ML at Dropbox, and formerly was an engineering director at Roblox. People among the audience who might have kids of any ages at this point might know what that is. Anyway, back to manufacturing. What this talk is about is recognizing that manufacturing is hard, and this is we always hear that this is like no better time to build hardware products and work in manufacturing space, but at the same time, it could be one of the most challenging times. And manufacturing space is immense and has a lot of exciting problems, which are marked in red here, drawn in red, maybe. And what we're going to explore is its relations to the booming AI technology shown on the other side, which also has a lot of kind of solutions to different problems. And they appear very quickly. It seems like every month or every couple of months, a new breakthrough happens. And both of those spaces are really hard to navigate. It takes AI experts full time to try to keep up with a part of the AI space. And what we're gonna try to cover is when you're doing manufacturing, when you're like an executive in a space, how do you take advantage and how do you navigate what solution could help me with a particular problem? How do you use all of this goodness? And what we find, the critical question that kind of on the high level that you need to make, for which problem does it even make sense to invest to see if there's AI solution available, how good it would be. So this is like kind of pinpointing what are the pieces that fit is like a key ingredient for success. And a lot of this has to start with the manufacturing side, because like AI experts don't know enough about the specific domain. So we're going to try to kind of outline this AI space, not going into too much detail, on a higher level in a way that makes it easier to evaluate what is the good problem to invest in, what is the good candidate to invest in an AI technology to get to a good result. We're going to do this by kind of, as I mentioned, by looking from a higher level, and instead of looking at details of what AI space has and what is like deep learning and neural networks, but on a higher level, and like what are the functional paradigms that let us think about this without having to understand a lot of the fascinating details of what that are emerging. Couple of disclaimers before we start. What we're going to talk is by necessity a simplified picture of what's happening in a space. It's useful, not comprehensive, so don't be surprised that some things like you'll hear like a latest something that contradicts. In general, we're going to try to keep it more production ready rather than kind of the latest and greatest and cutting edge that has to prove itself out. And finally, kind of the terminology part that I wanted to cover. There's like people refer and use terms of machine learning and artificial intelligence interchangeably. I think if you look at the formalistic part about it, is like artificial intelligence is the umbrella term for many technologies that bring it forward. But since the recent development, like it was all of the progress in AI was powered by machine learning, people use them interchangeably. I'm not gonna be religious about it. Like basically kind of trying to use what's more appropriate, but that's kind of the layout of the space. Here's what we're going to cover in this talk in detail. We're going to talk about two paradigms of using AI relevant to the manufacturing space, but many other spaces as well, supervised and unsupervised. We're going to talk about key factors for each of the paradigms. How do you evaluate the viability of a particular application, which which makes it easier to make this key investment decision. And we'll go through some examples of how to apply this in practice. One thing that we'll not cover in a lot of detail is like build versus buy, as in how do you proceed after finding a useful place to invest, how do you actually proceed in building a solution? 2 words I want to say about this upfront is, well, hopefully this framework will give you some idea of how to do like pre-work and validate that this approach, like this direction of like solving a specific thing would be successful. But by the time you kind of actually building some like automated solutions requires a lot of expertise. So at that point, you really kind of, after you identified like a worthy investment, it makes sense to engage with either for a one-off project, a consultant or a vendor with a product when you want like a repeated machine learning like models being trained and applied, because it does require a lot of expertise in ML and software engineering and all of the related things. All right, so let's dive into it. The main paradigms of the AI. The important set of context that will inform a lot of the restrictions and a lot of the reasons for some key factors exist is there's this inherent trade-off in machine learning models between how powerful the model is and how explainable is the output. Like how explainable is to why the model produced a particular result, why AI delivered a particular result. And there's a spectrum. And generally, the more powerful the model is, turns out it's less explainable of why and how it does what it does. And as we go, as you look at the progress, we're drifting towards using more and more powerful models, which are harder to explain. Again, this is a simplification and a generalization. There's some parts of the industry where explainable has to have, and this kind of they have to work with this constraint. But in general, we're going on this curve, which has significant implications of how do you both the paradigms on how you apply AI. And let's look what that means. So the first paradigm that we're going to cover is so-called supervised, which is you're building an AI model for automating a known use case. So the way to think about this is what AI does, it's a machine marked in orange here, where you give it a particular input and it produces a particular kind of predictable output. And this input has to be the same shape. So machine always receives the same things, could be images or text or a set of numbers, and would produce an output also of a predictable kind of shape and type. Maybe it's pass-fail. Maybe it's an output image. Maybe it's also a set of numbers. But you're defining your problem as, okay, I have a set of I have a predictable input, and I want a predictable output. So there's an image, and you want to figure out whether it's pass or fail. I'm going to kind of build this machine that takes and produces it. The way you create this machine or build this machine is less of a physical building and less of a programming by giving it rules, but instead you let the machine, you have a lot of data of what are those inputs and outputs, like a lot of examples, and you do some number crunching, like machine learning thing that produces a machine, from that data produces the machine that was learned to receive an input and kind of produce something close as what's in the data on as an output. So since you don't know, talking about what we had before, how exactly does it do it? There's very little glimpse on how exactly does it do it. The only way to make sure that this machine even works or does something that's expected is by having a separate test of data, set of data, which this machine did not see during the training, also inputs and outputs, and check. You feed those inputs to the machine that were produced by the previous process and check what it output it, like what's the output versus the expected. And that's pretty much the only way to check that your machine is actually doing what it's supposed to do. There's very little like ways to look inside and validate it in any other way. So this train and test data, both inputs and outputs, form what we call kind of input-output data set. And turns out that this data determines many things about application and is critical to success. This type of data, meaning whether it's images or text or something, this determines what is the machine learning algorithm or a model to use. The trained data, as we discussed before, kind of sets the parameters of this model. But more importantly, the quality of this data drives success. Like if this data that you use to train and test your models is garbage, it doesn't matter what it's going to produce, right? You're not going to be able to validate. It's going to blow up when you try to start applying this in practice. So when we switch into, okay, what are the key factors that determines the success in this case? For the supervised case, it's the quality of the data. And that means that it has to be clean, consistent, representative, and there's enough of it. And let's go through what this means for the in the manufacturing setting. One thing I want to note is I'm going to try to make examples realistic and relevant to manufacturing, which means it's extremely hard data to find. So I'm going to be mostly using instrumentals data because we happen to have a lot of like exposure to the manufacturing data, but we'll try to do it get from other domains as well. So having said that, what clean means is like imagine that your inputs and output is an image and whether it's a defect or not. And here we're talking about missing screws. So input is an image, output that you want to kind of create a model for is pass fail. And clean just means that there are no mistakes in this data. And as you can see here, okay, a lot of times the image, that's all pass and having no screws is fail. But this one, there's no screw, but it's marked as pass. And if you have a lot of mistakes like this, this would means that you will not be able to train model like a good solution, and you would not able to validate whether what you have is good or not, which could be even more important. The second part of quality of the data is how consistent that is. And what this means is that all of those, usually outputs, are marked using the same criteria. And it's especially hard when this output pass-fail comes from human experts and multiple human experts. So here's a case when there's a screw, there's some kind of contamination, and there's a question of should AI fail this unit or not? And what you might imagine, different people might have different opinions on this. Okay, some of them are really easy. Okay, the bottom row, probably okay. This one, definitely bad. But then we get into the gray zone, and different people might have different opinion. And what's even worse is we found that the same person might have different opinion over time. They might have one opinion in the morning and another one in the evening. And kind of seeing kind of this pattern of, it's really hard to say, and people are unable to be consistent about saying what's pass and what's fail, is also like a sign that your data will not be a good quality. Finally, and this may be the most challenging one, the data has to be representative. And what this means is the data should encompass all of the variation, all of the expected variation that it will see in practice, and particularly important for the test data that you use to validate that this machine even does what it's supposed to. And those examples of where you train data in one case, but then you're running in a very different setting is numerous in machine learning space. This is like the main horror story that people tell. The very kind of maybe innocent example of the story, like illustrated here, where people trained model to distinguish between huskies and wolves. And the way they did this is like just Googled a bunch of images of huskies and a bunch of images of wolves and trained a model to separate. And it turns out that most of the pictures that you would Google for husky is in people's home or with people or like something like this. And wolves are out there in the wild and they're outdoor and there are no people around them. And turns out that the model learned to check for that because it's much easier than like really understanding the visual difference. And this is an example of like a image of the husky outdoors with no humans around, and that was classified as a wolf. This is the most, again, kind of innocent example, but you can imagine like harder things like you look at COVID cases and try to train an AI to determine whether there's a good chance that someone's like exposed or not, or the severity. And if you don't get your data right, that becomes like a big danger. Rule of thumb of how to fix this, like what's the way to like combat maybe the most important issue on this path, is invest in getting test data in exactly the same place that you would apply the system for. Like here, would it mean if you want to use the system to like distinguish between like husky and wolves at like a place where both could be present, get some data from there, like realistic, and use that to check and evaluate the model. Finally, there should be enough of it. And this is one thing that's hard to evaluate as a non-expert. But once you know the use case, you can ask your vendor if ML expert. And one thing, like we've seen like a really big variance. For example, like we've invested in technology that lets you train a model to find defective defects with just 4 defective examples. And we've seen like other versions of this tech that could be maybe less like tuned for different use cases where it requires hundreds. So ask. All right, summary so far. We looked at the supervised, one of the main paradigms, supervised. The key factor is here quality of data, and it has to be clean, consistent, representative. There should be enough of it. The good news for you guys is that for most of them, you don't really have to be an ML expert to evaluate. Seeing how consistent it is, how representative it is of the actual thing that you'll see in real world with it is actually easier to be like do as a domain, as a manufacturing expert, because ML experts will not know or understand what is the SKU contamination that's expected in practice and what's good and what's bad. So the next paradigm that we're going to look at is unsupervised. And unsupervised is a setting where you have a lot of data. It may be not structured in a specific case. You don't know what are the inputs, what are the outputs, but you want to explore and find new things unknown for you and find like an insight that lets you understand something useful about this data. An example that we're going to use here is, let's say you have like a pile of Lego bricks or different kind of colored, different shaped bricks, and you can see the whole pile, and you want to understand something, kind of new things about it that you didn't know before. And the critical part here, there's a lot of, again, algorithms and methods to do this, but one thing to look at is how, like, so AI will understand some hidden structure of this data, but how it would present it to you, like what will you see in the end that would let you figure out, like find this, like learn new things. The typical examples go like this. One of them could be grouping. So AI could group them based on some kind of similarity. For example, here might be the color. You usually don't control what is the, what is the criteria. You just will try to find kind of semantically similar objects. And this would can give you an example, like kind of insight of how many colors do you have and how many pieces of a specific color. Another common one when you're looking for new things is ranking samples by either anomaly, means how unusual they are, or by relation to a particular kind of target point or maybe a set of target points. So here it could be, okay, find me the most unusual bricks. And you might find out that, oh, you have like very rare colors, or some bricks are very small, or like have a different kind of shading. And relating to the target, you can say something like, okay, here's a long blue brick. What are the most similar to it? or what are the most related, and you might get an idea of how many of other stuff like this like happens in the data set. Again, the critical thing, as we talked before, this is the output that you're going to get. It would be very hard, if not impossible, to interrogate AI why exactly this is the reason. Like, why this is more anomalous than other? Why was grouping done by colors and things like that? So whatever insight that you're trying to get has to be just by looking at this kind of output. And this brings us to the main challenge and a key factor of how those kind of use cases for AI, pan out or not. This is whether the output is useful. Here, similar kind of key factors to evaluate, how, like, what are the chances that it's going to be useful. One that comes up is how rich are the samples of your data. And the difference is, for example, if your kind of data that you feed is just a single number, maybe over time, this is like a run rate of the number of units produced, and the AI identified some portion of it as anomalous, and you're just looking at it, how easy is it to understand, is this even a problem? Understand more about the, is this insightful or how useful it is. If it's a single number, you can imagine, okay, yeah, it's happening. It happened again after. It's a single number. There's like a lot of investigation to even understand if it's worth looking into. And to contrast this, imagine that your input data is images, and this is what we kind of images sorted by anomalousness on a particular part of the unit. And you can see how, oh man, there's a screw here that clearly should not supposed to, it's like a loose screw. And that's probably a big problem. Or you can look at this contamination and kind of understand from the first principles whether it's a big problem or not. Finally, the other criteria that determines whether the output is useful is how much can it let you bring your external context of knowing what's good, what's bad, and let you explore the data rather than just trying to requiring AI to come up with the final decision. An example here is we have a functionality at Instrumental which lets people find unknown novel defects by ranking images of how anomalous they are, and we're showing which part of the units are anomalous. And what this lets people do is use their background and skim through a lot of data to figure out whether, okay, is this worthy defect? Is this contamination, or is this glue path, or like this some little damage? Is it a defect or not? If you would frame it as for AI to really determine, like just send me the list of defects, that makes the task much harder, if not impossible. But by showing you rich visuals, like rich samples, and in a setting where there's a lot of context around it, and you let people explore this, look at it, play with it, this lets kind of experts bring the external context that makes it much more useful. So this brings us to the framework to evaluate AI technology promising for a particular application. If you have an application in mind, first question to ask is, does it fall into supervised, meaning automating known, or unsupervised, meaning that exploring the unknown paradigm? And depending on what it is, run through the key factors to evaluate the chance of success. If most of them check out, all right, makes sense to explore it. If you see kind of big red flags on multiple here, then it's probably try to either reframe it or look for a different application. The maybe important thing to highlight that in both settings, your domain expertise in manufacturing is key part of the success. In supervised, it's making sure the data is consistent and representative, and it's chosen the framing of the problem chosen well. In the unsupervised, is making sure that the data, that this output that you're going to see from the algorithm will actually be useful for getting the insights that you're planning to get. And it will be you getting the insight. Like AI will only like show you some things, but the real value will be you understanding things from it and bringing into your process. So good news, it's like key risks are easy to evaluate. Well, not easy, but you don't have to be a ML expert to evaluate the key risks. But maybe more importantly, your domain expertise in manufacturing and building your products remains your competitive advantage because it's a key ingredient in both cases, and it lets you build on it rather than have a risk that AI would replace your expertise. All right, now let's make it practical, and we're gonna try to use this framework to evaluate together a few examples of potentially using AI tech. The way it's going to work is I'll read through the examples and what we want to do and what is the data, and this is a cheat sheet. So first task is to find out whether it's determine whether it's supervised or unsupervised, and try to get through some of them and evaluate kind of promising, non-promising. I'm going to wait for a couple of seconds after reading it and show you what kind of at least my answer is would be for something like this. So first one, I think it's kind of being talked in some framing from time to time, is we'd like the AI to analyze the historical test data and deliver actionable insights that we can use for designing the next-gen product. And our data for this is all of the functional rel and returns numeric data that we got from the current product, and would like to use it to gain insights for designing the next product. So here's what I think. So it does look like an unsupervised problem, right? We have a lot of data and would like to have insights that we don't know about. Our data is numeric, which means it's not super rich. Like even if I show you some kind of grouping or ranking on this, it would be hard to kind of get it into the kind of actionable insight. And it sounds like we want the AI to deliver the insight rather than bringing our external context or letting experts to play that data with the AI assisted way. So not promising. Look for a better framing. As an example of an alternative framing of a similar problem, we'd like AI to measure key dimensions and gaps of the units we build so we have a better idea about the tolerances we need in practice. And our data is images of all of the units built and point-to-point measurements performed by humans on a random sample of those images. So choose between supervised and unsupervised and go through the checkboxes. Okay, so it looks like supervised data. It seems that it should be pretty clean because point-to-point measurements are pretty should be consistent as well. It's representative because we have all of the data already, so we're doing a random sample from the data that we've built. If there's enough of it is kind of a question mark, but seems promising because it seems we have all of the data there and we have a lot of historical data. So far, so good. Next one is also close to many people's hearts, including us. AUI for a specific defect. We'd like to use AI to replace humans who check defective units online in real time for a specific visual defect where it's hard to detect it with traditional computer vision. Our data is images from pre-MP builds labeled by human operators. Sorry for the typo. Okay, so supervised, right? Because there's inputs and outputs. There's questions on consistency and how clean it is because humans do it for a complicated defect. And we've seen, even experts disagree. But for operators, it could be a concern. So we really need to check this. We're likely to be good on representative because this is from pre-MP builds of the same product. So should be same variance. Enough of it is a question mark that you need to particularly important here, because it could be that it's a limited number of the units that you deal pre-MP, and I don't know how many defects. So this got to check with an expert on, does this seem promising? So overall, both kind of it's kind of a middle of the road. Some key questions to answer, but depending on them, I think both good and bad might be valid. Just 2 examples left. One is finding bad glue based on images, where we'd like to AI to assist mechanical engineers with finding bad glue variations by choosing the most unusual photos to review. And our data, just images of the units and nothing else. So supervised or unsupervised, and likely to succeed. Okay, so since we don't know what we're looking for, we want bad glue variations, but we don't know what those variations are. It's an unsupervised setting. We have rich data like images, good. And it seems that we're like to bring mechanical engineers in the process and just want to assist them in being more efficient and reviewing them. So they'll be able to bring their context in. So looks good. This is actually one of the first, something like this was one of the first AI features that we've built at Instrumental. And with this kind of evaluation and framework in mind, that we might get a good chance to succeed because of those factors. Finally, would like AI to find chip paint on the tractors based on the close-up photos representatives on the field will send us. And our data is photos of one tractor we have access right now and has some chip paint. But all of the tractors that were built are the same color. Okay, so sounds like supervised. We know what we're looking for. We have some examples. It's likely that the data from this one tractor that we have will be clean and consistent. We will all agree of what are the chip paints. There is significant risk in how representative it is. Because okay, yes, they're the same color, but they may have very different chip paint patterns or a different use case. So the photos that representatives will send us could be very different from the ones that we will take, because we're going to have our own assumptions into it. And it doesn't sound like we invested in getting a test data from the realistic photos that representatives will send us to even evaluate how good our model will be. And it's unlikely that there's enough of it because of the reasons we talked about before. So overall, in this framing, unlikely to succeed. This brings us to the end of the talk. Thanks again for your time.